In this video, we're going to discuss solubility. When we want to get one material to dissolve in another, how does that happen? What governs it? How does it go? In general, we're thinking about solubility in aqueous material. Truth is, you can dissolve things in lots of other materials. You can get gases and solids, liquids into solids, liquids into liquids, gases into liquids, gases. Most of the time in chemistry, when we're working with things, we work with aqueous solutions. So let's talk about in water. Water is exceptionally good at solvating many different types of things, especially if they are polar in any form. And so water tends to solubilize ionic material very well. To do this, you'll have your solid ionic material nicely attracted to the opposite charges in its lattice, and a water molecule will approach. Well, there's a partially negative and some partial positives on water, and those partial negatives can interact with the cation, and those partial positives can interact with the anion. One water molecule on its own isn't enough to overcome the attractive forces of the other ions, but there's a lot of waters. And so bit by bit, these attractive forces can stack up, and it can become favorable for that ion to break free and be solvated, to be surrounded by waters. And while the full positive, full negative attractive force in the ion is greater than the partial negative and a full positive, or the partial positive and full negative of the water solvating the ion, accumulating many, many waters can add up to be far greater. Depending on the relative strengths of the water solvating versus the ion-ion interaction, this can be exothermic or endothermic. But many, many ions are exothermic. They break apart, form more total strong bonds to water, and give off energy in the process. This is fairly favorable in dissolving away materials. But it's also key for how we have to think about why water solvates things. The individual water molecules are directly interacting with what they are solvating. In fact, you can have many, many water molecules surrounding a single ion. Because those water molecules are kind of well held in place, there's actually layers. Another layer of water molecules tends to kind of line up, also supporting and interacting with the existing water molecules that are directly connected to the ion. And so we have some shells of solvation. Technically, this is an equilibrium process. It is possible for those ions, if the whole shell bounces back into solid, to readhere, to get trapped and stuck back onto the solid. This is actually part of why there's a max solubility in things. If I have a beaker and it has some salt content at the bottom, and I've got some water, it starts to break apart. It starts to drift off into the water. And so you start to get ions floating around in the water, and my solid gets smaller. It's possible you can dissolve all your solid, and it will be nicely dissolved in water. But if you've ever made sweet tea or just had a whole lot of salt in water, it's also possible you get to the point where no matter how much stirring you do, the remaining solid at the bottom does not go away. This would be the max solubility. It is possible to saturate a solution, which just means to get the max dissolved possible. Why is there a max? Well, even though you've got those ions floating around out there, there is a chance they will bounce back into the solid. And so this is kind of an argument of there's a leave rate, how fast your material leaves the solid, and the more of it that's in solution, the more likely one of those ions is to stick to the solid again. So there's a return rate. Initially, the return is really small. But as you get more and more material to dissolve, there's more ions, there's more chances, and eventually the return rate is equal to the leave rate. At some point, you just can't actually get more material to dissolve. Now, how much will be dissolved? Well, it's kind of based on the leave rate, which is based on the energetics of how favorable it is to dissolve. And so some things you can dissolve far more before you reach its maximum. Some things you can dissolve far less. In 163, you'll eventually get to KSPs and the max solubilities of things, but this is just the general idea of what's going on mechanically as we're dissolving these ions. This is true not just for ions, any material that it's solvating. If you've got methanol, well, that's a pretty negative oxygen, it's a pretty positive hydrogen, it's even a little bit positive carbon there. Water can interact with that. Water can pull up, have a pretty good interactions between various parts of the water and the alcohol. And so even though you've got carbon and hydrogen, which is not a polar bond, if there are polar parts on the molecule, water can interact with it. Small alcohols like methanol and ethanol and propanol dissolve quite readily in water. However, as you get larger and larger carbon chains, say 5 carbons to an O to an H, and lots of hydrogens I don't want to draw. Well, eventually, while water can indeed interact fairly nicely with this part, down here where that OH is, the waters near the rest just don't have good interactions. Those hydrogens on those carbons aren't polar. And so any waters that are stuck along this chain basically have a chunk of space where they don't interact strongly with anything. This is sort of a surface of lower interactions. Any of those waters that can instead move back to where there's other waters more and kind of get on the inside are going to have significantly better attractive forces, and they're not going to want to go back and interact with that carbon chain. As a result, the more carbons and hydrogens your molecule has, the more nonpolar it is, the less water can dissolve it. This is why oils don't dissolve in water. Oil is a very nonpolar molecule. The preference for water is to leave it, go back and bounce into other waters and stick to them. And so bit by bit, if you had a bunch of oil molecules, and you may have seen this in, say, salad dressing. You have a salad dressing bottle, you shake it up, you get lots of little droplets of oil mixed in with your water. And well, this water isn't very strongly bound to the oil, so it moves around, and if it happens to drift out and get strongly interacting with the other waters, it's not likely to go back between the oil droplets. And so randomly over time, the water tends to move out more often than it moves in. The oil gets squished together, and bit by bit, eventually your oil just kind of reaccumulates, and you get that oil layer on top. And so if you ever watched your salad dressing kind of separate itself after you shake it up, this is what's going on. These intermolecular forces are not favoring the water dissolving those carbon chains. It can handle it if there's a little bit of carbon chain versus the amount of attractive force, but it can't really handle it if there's a lot of carbon chain versus a little attractive force. And so some things dissolve nicely in water and others don't. It comes down to these intermolecular attractions again. Well, you can have things that don't dissolve nicely at all. You can have things that max out their solubility, but there's a few other tricks that come along. Solubility is also temperature dependent. If you have more available energy around, it's more likely that your water molecules are able to slam into your solid and knock one of your solids free. It takes a little bit of work to break it off so it can wrap around. The hotter it is, in general, the more you can dissolve, because they're impacting, you're increasing the leave rate effectively, which means you need more in solution before you max out. And so often, for ionic compounds, an increase in temp leads to an increase in solubility. This is not a 100% rule, but it is generally true. This tends to be true also for small soluble molecules. The increase in temp will lead to an increase in solubility. However, you can also dissolve gases. If I've got gas, every once in a while a gas molecule hits the surface and kind of burrows inside a little bit. It then gets surrounded by water. And so you can have something like O2, which is a dioxygen molecule. It's got a fairly uniform electron cloud. But when water comes up to interact with it, water has a somewhat negative. And so somewhere on the other side, there's a water with some hydrogen's pointing to it, somewhat positive, that electron cloud tends to get polarized. It tends to shift. As there's now outside influences pushing electrons away and pulling them towards opposite sides, electrons around a molecule are somewhat malleable. Smaller molecules can do this reasonably well. Our larger oils couldn't do it phenomenally well until water separated, but small amounts of gases can do this reasonably okay. They're also just largely surrounded by water. It takes a while for that gas molecule to randomly move and work its way back out. So as a result, you can get a little bit of gas dissolved in your water or any other liquid. However, this is not particularly favorable. Gases, by their nature, want to be spread out, not interacting with things. They already have enough energy to break free from all their normal attractive forces. So in general, if you heat them up, as the temperature goes up, the solubility goes down for a gas. Because now it has even more energy, it moves even faster, and it can break what little weak induced dipoles were formed much more easily. And so as you increase the temp of gas, you tend to lower its solubility. It goes opposite of our ionic materials and our small polar molecules. Well, temperature can raise the solubility, which leads to our last neat trick. Let's say I start at a high temp, 90 degrees Celsius, and I have a lot of material dissolved. In fact, I dissolved all of some amount of material. But then I cool it down. I bring it down to 30 degrees Celsius. Well, it's possible at 30 degrees Celsius, I can't have that much in solution. The maximum amount at 30 degrees Celsius might be only that amount, which means a lot of it had to turn solid. This is precipitation, and this actually is a handy tool. We use it in chemistry and in industry to purify materials all the time. You heat up your solution, you dissolve everything because it gets more soluble as it dissolves, and then you cool it down, and some amount of it can no longer stay dissolved and begins collecting and crashing out of solution. This is a handy way to get small impurities to dissolve. In your original solid, you might have a small amount of an impurity that if you can break out of the solid and get dissolved, well, it will still be completely dissolved at the lower temperature. At 30 degrees Celsius, that small amount of the impurity is still fully soluble. We haven't reached its limit. And so you can get your impurities to stay out. You can then filter this, and the solid that you collect is much more pure. And so we can exploit solubility properties as well for a lot of industrial processes. To form these solids doesn't actually naturally occur. Remember, we talked about an ion pairing back up with other ions, and well, if they're all still floating around in water shells, there's not really an exposed ion to make that happen. A lot of times, if you start to cool, it doesn't instantly form solids. Something has to trigger it. We call it a nucleation site or nucleation event. But some nucleation occurrence must happen where, for some reason, for various properties, or maybe a little bit of a crystal that already existed, there's an edge, a material for the ions to start sticking to. Once that exists, anything that bumps into it can stick to it and it starts to grow. Some materials are really bad at doing this, and in fact, you can cool it down, and for some materials, everything will stay in solution until you give it a nucleation event, in which case it all crashes out really rapidly. These are supersaturated solutions. These are when you have more than the max. It just takes time for things to transition from being solvated to not being solvated. They will do it over time. Eventually they will fall out, but some of them can be very difficult. You may have seen videos for this, in fact, with a similar event with frozen water. If you put a distilled deionized water bottle in your freezer, and you take it out when it's cold enough, you can still have it be water, but you slam it on the table and it turns ice. You can just watch the ice crystals form. It's a similar idea. Transitioning from one phase to the next requires some physical modifications that don't necessarily happen easily without a nucleation event or a nucleation site. A sudden impact creating extra density can cause it in your below zero freezing water. A quick shake of your flask or a scraping on the side to slightly mark up the glass surface can cause it in a beaker full of dissolved material. This all comes back to equilibrium, though. Molecular attractions have to find each other, have the time to interact. None of this necessarily happens instantly. But if you allow things to reach equilibrium, if you give them the time, these are the properties we expect to see from them.